created naturally and ozone is destroyed naturally. Ozone is created by sunlight. How? When oxygen absorbs a light of less than 240 nanometers, it splits into two oxygen atoms, O plus O. And that oxygen atom plus oxygen, it combines to give a molecule of ozone. So that means how it is created? By sunlight. Because we are getting this radiation, UV radiation from the sunlight. How it is destroyed? It is also destroyed by solar radiation. How? Ozone takes another electromagnetic radiation with a wavelength of less than 320 nanometers, and it splits into oxygen and oxygen atom, oxygen molecule and oxygen atom. And this one oxygen atom, it combines with ozone to give two molecules of O2. Sorry, there should be a two here. So, but your chemist, you understanding how that is. So that means we get oxygen. So that means it is being created by nature, created by sunlight, destroyed by sunlight, and we say, oh, we are doing this and that. Then why there is such big thing? Yes, there is a big thing. One thing, ozone is very, very reactive. It reacts with many chemicals, including chlorine, bromine, hydrogen, right? And important thing is both these reactions, that is the natural creation and natural destruction. These two reaction sequences together with many other more complex ones, they balance to give an average of around 300 du. Du is Dobson unit. Like you measure distance in kilometers, right? Weight in kilograms. So similarly, we measure the level of ozone in Dobson units. Dobson unit is a little complex. I would say that 1 parts per million is almost 0.65 Dobson units. Or you can say 1 Dobson unit is that if you bring all the ozone at 0 degree near the atmosphere, near the earth, and if you can have it thickness of 0.01 millimeter, then it is 1 Dobson. But we can say that this is a unit. So together, natural creation, natural destruction, it maintains a level of about 300 Dobson units, which is sufficient. That 300 Dobson units protects all UVC from reaching us and protects more than 95% of UVB from reaching us. I can explain it with a simple cartoon. Let us say this is again you see to see the perspective, the tongue of the radiation. Right. Now you see, suppose this is a bucket and this is the sunlight. This is the sun. So sun is producing ozone. So it is filling the bucket. And let us say, think about only these two holes to the right, which are natural destruction. That means our oxides of nitrogen, hydrogen, chlorine. So these are natural chemicals. I'm not talking about man-made chemicals. So natural. So there are two natural holes. So you understand what is equilibrium. So that means sun is filling the bucket. There are two holes which are taking out. Depending upon how much is being filled, how much is taking out, there would be an equilibrium. So suppose there is an equilibrium. So that means there would be a particular level that will be fixed in the bucket. So the same is that if this level stays 300 Dobson units, we have. The problem comes that if nature made this 300 Dobson unit of equilibrium and we put another man-made hole, the moment we put another man-made hole, the equilibrium would be disturbed. And when the equilibrium would be disturbed, what will happen? Immediately you see the ozone column would keep on getting down. So we'll have less than 300 Dobson units. And that is when the problem starts. So that means it is being created and destroyed naturally. But the moment we interfere as human beings, that is where the problem starts. And it is maximum in the stratosphere at about 25 kilometers. And this is how it blocks. It blocks complete whole of the UVC, about 95% of UVB. And it doesn't block UVA. UVA reaches us because we need it. Right? So above in the stratosphere, it is very good. And in the troposphere, it is not good. So now we understand that ozone is important and hole is a very bad. So if we talk about the discovery of ozone hole, then this is one of the most important scientific findings at the end of the last century. Most important. It was first discovered in 1985. In the background is the picture that we are flying the Indian flag on 26th January on our ship. Right? So it was first discovered in 1985 over Antarctica. And when it was found, scientists couldn't believe what they found. They didn't publish it. They thought that their instruments are bad. They waited for 1 full year. New instruments were flown. Again checked. And then they were surprised. Oh, such a loss of ozone. Only then they published. They checked the data with the TOMS. TOMS was a satellite, total ozone mapping spectrometer, that was measuring it from the space. And they found no, TOMS was not showing, the satellite was not showing that ozone is depleting. So they said, no, something's wrong with the instrument. Then next year again the instruments found the same, and TOMS was showing no. Then they found the raw data and found that because nobody believed that the ozone can go such low levels. So who would go in the satellite to change it? So they felt that okay, if the level of ozone, if the reading of ozone is less than this, disregard it. If it is more than this, disregard it. That's why it was not showing. And when they checked the raw data, they were infrared that was also showing the low levels of ozone. So it was first discovered in 85. It is characterized by a rapid depletion of ozone over Antarctica during spring. It is not a whole year phenomenon. So there is a season. The season is from August to October, and by late November or late mid-December, again we have the complete ozone back. Now there is no ozone, and you can say, so what? No, but there is a big what. And ozone hole, now we know, is caused by the chlorofluorocarbons, because we know that it was not present in 1970s. Because we started measuring the level of ozone in Antarctica from 1956. So from 1956, you see, up to about 1970, you see the ozone level was around 250 to 300 or 250 to 325 Dobson units. But after that, it kept on decreasing. And we found it here around 1985. And you can see for some years it was getting worse, but now it is again starting to get a little better. And everything what I say, to understand that why it happens in ozone in an Antarctic spring and not the whole year, you can see by this one simulation. Now please pay attention before I start it. Here you see, you look here, the time is going on. This is talking about the total ozone in Dobson units. Like right now you see it is 270, 260, 270 Dobson units. And this right side is showing the polar temperature. This is the simulation from the data of 2022. So you can see that here, right now in January 1, the temperature is around, you can say minus 60, minus 58 degrees Celsius, right? And now you just try to see what is the relation between temperature, time, and Dobson units and the ozone. So you see March, still it is comfortable between 200 and 300, temperature is going down. Now you see it came to minus 80, minus 85, May, June, because it's the Antarctic winter. So still you see it is perfect, around 250. And suddenly you see now came August, the temperature would start to increase a little bit, you see. And the moment it starts to increase a little bit, it goes to minus 70 or something, it came down. By December, again you see. So that means when the temperature is going down, ozone is stable. When temperature starts to increase, the increase is from minus 89 to, let us say, minus 80, minus 79, minus 70. We're not talking about plus 18. That means Antarctic spring. Suddenly you see there is a loss in the ozone. Huge loss in ozone. And we have huge, big ozone hole over Antarctica, which once it has also gone to over a part of Australia for 1 year. So now keep in mind that means there is a relationship between temperature, time, and the ozone. Now what does that mean, the discovery of ozone hole? It simply means that our understanding of the atmosphere is far from complete, although we may say, oh, we know our science has progressed this much, but still we are not very close to it. So now why there is ozone hole over Antarctica? We know it is destroyed by the CFCs, but there is no relationship, there is no production in Antarctica. And the picture that I showed you where this is the whole stuff, my stuff, which was in the sling. So you can say this is the sling, all of this will go into the sling, and I'll go inside, and the stuff will go down. That is how we transport. So in Antarctica, our major transportation source, like here in any other city, you see in India, the local transportation is just by auto. For a common man, auto rickshaw, 3-wheelers. So in Antarctica, this is our 3-wheeler. Only the chopper or the snowmobile. We cannot move without that. So why there is a hole in ozone? We know it is because of chlorofluorocarbons. What are chlorofluorocarbons? As the name suggests, they contain chlorine, fluorine, and carbon. They are long-lived. Once when they were made by General Motors, they were named as wonder chemicals. You see, there were so many awards were won by General Motors. At that time, the newspapers were filled by, because they have no odor, they are non-reactive, they are very long-lived, as much as 100 years. So in 60s they were used in refrigerators, air conditioners, especially you see if you remember from your younger days, there used to be a gas called Freon. So Freon basically is a CFC12. So that was the main ingredient in your compressors, all your you can say the refrigerations. So you can see that they are used mainly in refrigeration, phones, and aerosols and others. So, and there's a beautiful nomenclature of these chlorofluorocarbons like CFC 11, 12, 113, 114, 115. Beautiful nomenclature, and CFC 12, although all are combined also called freons, but CFC 12 was the most used, what we used to call as the freon. So we said that the CFCs, chlorofluorocarbons, are completely inert near the surface of Earth. They're non-reactive, they don't react with anything. But in the stratosphere, they destroy ozone. Why? How do they destroy ozone? For this also, ozone layer is responsible. That they destroy ozone in the stratosphere, but not in the troposphere. Now, how do they destroy ozone? Let us take the case of CFC113. This is also a freon. So, when this breaks down, any chlorofluorocarbons, we get a chlorine radical and other products. Once we get this chlorine radical, now this chlorine radical can react with ozone, and we get chlorine monoxide and oxygen. This chlorine monoxide can react with an oxygen atom, and we'll get a chlorine atom and O2. When you combine together, one chlorine radical will combine with one molecule of ozone, one atom of oxygen, we'll get two molecules of oxygen, and we'll get the chlorine radical back. So that means ozone molecule is destroyed, but the chlorine radical is as such. It's a catalytic reaction, you know, that is what happens in the catalytic reactions. So, why this catalytic reaction takes place only in Antarctica? Why not in the troposphere? Well, Antarctica is a huge continent, well, that's not the reason. It's larger than Europe and Australia, it's the fifth largest continent. And Antarctica is, you already know, it's the coldest, minus 89.4, windiest, 327 kilometers an hour. But there are so many other superlative adjectives associated with it. It is the highest continent. The average elevation is 7,100 feet. It is the coldest, windiest, and driest. Some of the valleys in Antarctica where it has not rained for 2 million years. And many missions to Mars, they are being tested in Antarctica, that is close to Mars. It is so dry. It's the driest continent. It's the most isolated continent, and technically it is classified as a desert. Right? Now, the answer lies in all these things. So, why only above the Antarctica? Why this catalytic reaction takes place only in Antarctica and not nowhere else? For this, the reason is the special conditions which exist only in Antarctica. Now, what are those special conditions? You see, in Antarctica, what happens? That the decomposition of chlorofluorocarbons, it makes chlorine, and that chlorine can react with many chemicals which are naturally present in the atmosphere. Like you see, it can make chlorine monoxide. Chlorine monoxide can react with nitrogen dioxide to produce chlorine nitrate. It can react with methane and nitrogen monoxide to produce HCl. Now, neither HCl nor chlorine nitrate, none of these can destroy ozone. But surprisingly, what happens that in Antarctica, we get these clouds because it is so, the temperature is so low, and these clouds are made up of not only of water but also of this hydrochloric acid. So that means there